Now we're going to look at relative motion, which is a way to describe the motion of an object in different reference frames. So I like my simple definition. This is often way overcomplicated. I'm going to show you an easy way to think about it. But my simple definition would be different values in different what is my simple definition? Reference frames. The thing is moving how it's moving. It's just how we describe it would depend on our frame of reference. Let's see. So I'm going to start, though, with really not getting into velocity. So we want to start easy. Let's start easy. Start easy with position. Right? You don't, often people want to jump straight to velocity for relative motion. No. Start with position. And let's consider the position vectors of Hal. Oh, actually, no, Hal's not here. Hal and Al are in couples therapy. Don't ask. Trust me. I have one of the plastics here. The position vector of the plastics, PL, in two frames. And the two frames are what we call the lab frame. So lab frame usually just refers to the building or the earth, the one that everybody feels like is stationary. So lab just means building, but usually we call it lab. It's nice and short. And the other frame we'll call prof. That means my frame. I was going to call it the Hafner frame. That felt too egotistical. I was going to call it the Jason frame. I thought you might be uncomfortable calling it that. So we'll go with prof frame, L frame and P frame. So the lab frame, we'll just draw our coordinate system like this. And we will say the main coordinate system, the one you always think about, X and Y, is the lab frame, which we'll abbreviate with an L. So if you imagine the origin of the lab frame is sort of here, right, in an XY plane along the floor, right? So there's the lab frame. I'm going to stand here, okay? I am at the origin of the professor frame at all times, right? The professor frame goes wherever I go. I go over here, professor frame goes over here. I go over here, professor frame goes over here. So I'm sort of at the other side. I'm going to stand right here. And it's really great to have a frame that just follows you around all the time. I highly recommend you get one. So this is the prof frame. Right. Now where's Hal in all this mess? Or I'm sorry, the plastic in all this mess. So there's the origin, here's me. Plastic's kind of up here, like that. There's the plastic. Plastic doesn't get a frame, right? He's part-time, right? So what we got to do is simply draw position vectors. Okay, we're going to draw three. First, we're going to draw, let's see, the R vector, like that. And that is the position of, oh dear, I called it H, but if I switch it to P, then P was professor, so Frank. I'm giving him a name. That plastic is named Frank. So, Frank. It's the heaviest plastic, that's how I remember. So this is the R, the vector of Frank, F, in the lab frame. Why is this the lab frame? Because it's drawn from the origin of the lab frame. We could also figure out where am I in the lab frame. We all care about that, right? R of the professor in the lab frame. So the first subscript is what it is, what position you're talking about. Second subscript is the frame. We could also think a little bit about Frank in my frame. Right? Let's draw that vector. Well, my frame is here. It's kind of to the left and up, right? So it's kind of over here and up. It's this vector right here, over and up. That is the position of Frank in P in my frame. So all we did was draw three position vectors. Nothing's even moving, right? Relative frames, you don't have to have things move. It's not that big a deal. But if you look at these, it also looks like we've added three vectors, right? You have R, professor lab frame, and then head to tail, you've added R, Frank in the professor's frame, and you get this vector, R, Frank in the lab frame. So you could write it like this. R, Frank in the lab. That vector is R, Frank in the professor frame, plus that vector, position vector, R, professor in the lab frame. But most of these problems don't involve positions. They involve velocities. You want to think about velocity. Well, guess what? All you got to do is take a derivative. And if any of these things start moving in time, or if they all start moving in time, this just becomes their velocities. The velocity of Frank in the lab frame is equal to the velocity of Frank in my frame, the professor frame, plus the velocity of me, the professor, in the lab frame. Okay. And most of our relative motion we talk about, soon we'll talk about inertial reference frames where they have to be zero acceleration. But if you want to get outside of that area, you could take another derivative. And what would you get? You'd get the relationship between their accelerations. The acceleration of Frank in the lab frame equals the acceleration of Frank in the professor frame plus the acceleration of the professor in the lab frame. So we got all of this just from this little position vector diagram. And really this is the one that you're going to use the most in problems, is the relative velocities. So we can kind of check it. If we imagine now, let's let things move. Let's think about this case. I'm standing here and I'm walking this way. And I look at Frank, and it looks like Frank is going positive velocity to the right. Well, let's think if that makes sense. Was Frank actually moving in the lab frame? No, that's zero. So, but I did move in the lab frame. I started moving in sort of the negative direction at 1 meter per second. So what would I have to observe Frank do? To make this true for 0 equals something minus 1, it has to be plus 1. And sure enough, that's what I see. If I walk this way 1 meter per second, I see Frank moving that way 1 meter per second. Now, some people have trouble envisioning their own frame of reference. They're so used to thinking about the ground. But for faculty, for professors, we're actually quite good at it, as you can imagine. So now what we're going to do is see how we can use this for typical physics problems. Now we're going to talk about what happened when Galileo went through puberty. No, just kidding. Now we're going to talk about the special case of uniform relative motion. So of course what that means is that all of the velocities are constant. Nothing is accelerating. Same thing it meant when we were doing kinematics problems. Uniform motion, nothing is accelerating. So the problem we're going to work on is a boat crossing a river. So here we've got the river, and the boat is trying to get to a dock. So there's the dock, there's the boat, there's the dock. This is the land, which is one of our frames, and this is the water, which is another frame. And they're different frames because the water is rushing to the side at 3 meters per second. So you can imagine the water represents, when the boat is in the water, it's a frame of reference moving at 3 meters per second that way. The boat, whenever it's in the water, it feels like it's going 5 meters per second this way. So relative to the water, the boat moves 5 meters per second up. Right? So if the boat just goes like that, one question we could ask is, by how much will it miss the dock? You could probably just do this intuitively with kinematics, but let's go ahead and look at the relative motion problem. Because the way you want to set up sort of a reference frame problem is you want to say, what am I looking for? What am I trying to get? What do I want? Right? You want the velocity vector for the boat in the land frame. You want BL, because we're trying to figure out how far it went relative to the land. Right? And the water we know just went north. All it knows is it went north. But the dock is connected to the land. Where it started is connected to the land. So we need to know how far it's really moving in the real frame, the land frame. So whenever you have what you want, all you got to do is write that equals V, the same symbol, and write the first one that you had. The first one you're looking for, dash. And then just go ahead and move over and say plus V, except make your V nice, like that. And then put the dash in what you're looking for, land, right? See, the BL just got split up into B and L. And then in between, you just stick what you're dealing with, the water. Ooh, subscript, like that. And then you always get the formula right. You want the velocity of the boat in the land frame? Well, that's the velocity of the boat in the water plus the velocity of the water in the land. It'll always work. So that's how you can remember how to set it up. Well, in this case, this one, everything is sort of perpendicular, so this one isn't too bad. The velocity of the boat in the land frame, boat in the water, is 5 meters per second I hat, basically. So you'd say 5 I hat, and it has no j hat component, no horizontal component. And the water is all j hat, right? So plus 3, I'm sorry, this was j, this isn't the y, that's backwards, right? J is the vertical, and the lateral, the horizontal, is 3 I hat. So this is y and this is x. So instantly then you get your velocity of the boat according to the land frame. It's just the sum of those two vectors, the vector sum. So if you wanted to solve that problem, how much will it miss the dock? Then you would probably just do sort of two one-dimensional problems. You'd say, how long is it in the water? Delta t would be, well, it's going 5 meters per second, and you got to know the width of the river, which I didn't tell you, which is 20 meters. Right? So it'd be 20 meters divided by 5 seconds. So 25 meters per second equals 4 seconds. So there's your y part. And then your x part is simply 4 seconds going 3 meters per second. So it's going to miss by 12 meters. Right? 4 times 3 equals 12 meters. So we set it up with a little relative motion, but we really didn't need it that badly. You could almost just do that one with 2 kinematics problems. Pretty much what we did. But here's a slightly more complicated question. If the boat wants to hit the dock, so this was question 1, here's question 2. To hit the dock, at what angle should he steer? What angle should the boat set out at relative to the water, relative to the perpendicular bank? So we could kind of draw it instead. We could say, oh, it's going to go off like that in an attempt to end up at the dock. So at what angle theta? Still 5 meters per second. That's what the motor does. But what angle should he turn off at? Well, let's see. You would still say we need to use this same equation. This is still the relevant equation. Velocity of the boat in the land is boat in the water plus water of the land. But let's see what we get. So the velocity of the boat relative to the land is, so velocity of the boat relative to the water, so we just have our two components. In this case, the x component is actually negative 5 meters per second sine theta. It's a little unusual. Minus 5 sine theta, I hat, plus, and then it's plus 5 cosine theta, j hat. So there is that one. And now the velocity of the water relative to the land is just 3 meters per second in the x direction. So plus 3 I hat. There it is. So here's your I hat components, and here's your j hat component of what the boat is doing. And then you got to go to the problem and say, what's it going to take to hit the dock? And basically what it's going to take is we need velocity, boat in the land, the x component to be 0. We could take this back to a position problem, but we don't really need to. If the x component is 0, it's just going to go straight like that. So you can actually solve it that way. So let's write this x component. It's minus 5 sine theta plus 3 has to equal 0. And the only unknown is theta. So sine theta equals 3/5. Sine theta equals 0.6. And theta then, if you take the inverse sine, is 36.9 degrees. So if the captain takes off at 36.9 degrees to the normal, it won't go like at a curve and get swept back. It will literally, the boat will be tilted and it'll just go north just like that and hit the dock.